Welcome back. So it's been a pretty interesting series of discussions on differential equations and dynamical systems. In the last few videos, I've shown you how to integrate differential equations and systems of differential equations, even if they're nonlinear. We can integrate them on a computer using numerical simulation techniques like Runge-Kutta schemes or Euler schemes. And I mentioned kind of in passing that there are certain systems that are chaotic systems that are especially hard to simulate, to integrate accurately forward in time, that kind of amplify uncertainty and errors, maybe even exponentially in forward time. And so today I'm going to dive in a little bit more to what I mean by chaos and chaotic systems. I'm going to give you some definitions and some examples, and we're also going to work out, kind of with math, some of the implications of what it means to be chaotic and how we can interpret these solutions, and also it'll give us an idea of what we might be able to do to improve our numerical algorithms to simulate these kinds of tricky systems. So this is a video, we actually coded this up in Python and MATLAB to simulate the Lorentz 1963 problem, this chaotic system of three differential equations. And what I did was I took an initial condition and added a cube of uncertainty, this red cube of uncertainty, and integrated all of those trajectories forward in time. And you can see that the trajectories initially stay together, but after a very short amount of time, they start to stretch and fold and mix onto this chaotic Lorentz attractor. And so this is kind of pictorial evidence of kind of the first main point I want to make, which is oftentimes chaos is defined as a system that has sensitive dependence on its initial conditions. So you can think of this red blob of uncertainty as some uncertainty in my initial condition, and very soon as I integrate this dynamical system, that uncertainty grows and grows and grows until, after some finite amount of time, those initial, that grid of particles could be anywhere on this attractor. This is in stark contrast to a non-chaotic system such as a pendulum or a mass on a spring, where even if the pendulum is nonlinear, it has nonlinear terms, theta double dot equals minus sine of theta, it still does not have this sensitive dependence on initial conditions. If I start with a blob of initial conditions around some nominal theta and I let all of those go, they're going to basically stay together in the same kind of clockwork, and there will be some predictability in the future based on those initial conditions, whereas in a chaotic system you truly have this sensitive dependence on initial conditions. And so that actually causes some big issues. So for example, when we talked about our numerical integrators, we were trying to find some numerical trajectory. Let's say, I have x naught, and then I want to integrate it forward to get some x1 and integrate that forward to x2 and so on and so forth. And we developed schemes like the Runge-Kutta scheme and analyzed the error properties at each time step. And so for example, we showed that, or at least we said, that the fourth order Runge-Kutta scheme has error that is on the order of delta t to the fifth power, where delta t is my time step. At every single step of the integrator, I have order delta t to the fifth error. Now, for deterministic systems, what you can do, this is what's called the so-called local error. This is kind of local at each dt, at each delta t. And for a deterministic system, not like this chaotic system, but more like the pendulum system, you can compute from this local error what is the global error across the trajectory. Because essentially these errors will just add up, and each time step you're accruing this order delta t to the fifth error, and the length of my trajectory, if I make delta t smaller, I have more steps for that to accrue. And so the global error is often just this number divided by delta t. So the global error would normally be order delta t to the fourth. Now, that's just not true for chaotic systems. This global error doesn't make sense for chaotic systems. I'm about to show you why. So this is not true for chaos or for chaotic systems. And the reason is because at each little time step, when I accrue this very, very small order delta t to the fifth error, so I have, I take one time step, and my simulated trajectory deviates from my true trajectory by some teeny tiny little epsilon. So instead of going to x1, I go to x1 plus epsilon. That epsilon, so I basically go to x1 plus epsilon. That's the error in my numerical scheme. It's teeny tiny. But over time, because of the sensitive dependence on initial conditions, because of a chaotic system, this epsilon is going to grow exponentially in forward time. So my trajectory, my simulated trajectory, and my true trajectory are going to diverge, even if I'm only introducing these teeny tiny little order delta t to the 5th errors at every time step. So the way that these local errors compound for chaotic systems is way, way worse than for non-chaotic systems. And so this notion of global error that we think of for pendula and spring mass dampers just doesn't apply to chaotic systems. It's much worse than that. You essentially have something like each of these little errors, these little local delta t errors at every time step, get magnified by some exponential function, some e to the lambda t, where lambda is a positive number called the Lyapunov exponent. Lyapunov exponent. And that essentially says that every single time step, these little errors are growing exponentially in time. And so this is going to motivate better integrators, or at least different integrators for these chaotic systems oftentimes. So for example, if I have a Hamiltonian system or some mechanical system governed by the Euler-Lagrange equations, there are special custom tailor-made integrators that are designed for those systems, if they're chaotic, to give you better properties and kind of stay on this solution manifold more faithfully. Okay, so I'll tell you about that a little bit more in a minute. I'll just mention here that Lyapunov, this is one of the most controversially spelled names in all of mathematics. I think I've seen at least 3 different spellings of Lyapunov. This is the one I grew up with, so this is the one I'm using. But when you Google Lyapunov, there's going to be like at least 3 different ways to spell this. And so often what we try to do is we try to use a small enough delta t that our Runge-Kutta error is actually very, very small to begin with. So order delta t to the 5th, we want that to be as close to machine precision as possible, 10 to the minus 12, 10 to the minus 16. But even if this epsilon is 10 to the minus 16, for a positive lambda, it doesn't take very long for this error to grow to order 1, to a big significant error in our simulation. And last thing I'll point out before I give you some examples is in this chaotic Lorentz system, because the trajectory is kind of bound to this white attractor, this is the so-called strange attractor or the Lorentz butterfly attractor, that epsilon grows initially exponentially, but then eventually the trajectory is still stuck adhering onto this this strange attractor. And so I can actually get away with using something like RK4 if all I care about is the rough shape of this attractor or the rough statistics of this attractor. Maybe I don't care if this is the exact perfect trajectory that initial condition would take. This is a representative trajectory because it's going to do the representative thing on this Lorentz system. If I wanted a very quantitatively accurate trajectory that followed the exact true dynamics, I might need to use something more fancy than a Runge-Kutta scheme. So we'll come back to this in a minute and we'll talk more about these kind of numerical considerations. So the other examples I like to think about, so this is kind of one of our canonical simplest examples. It's a 3-state ODE that happens to be chaotic. The solar system is another great example. So chaos was actually discovered, or at least kind of codified mathematically by Henri Poincaré in the early 1900s. I think it might have been 1906. Right around the time Einstein was making his great discoveries, Poincaré was kind of solidifying this theory of chaotic dynamical systems. And actually a lot of the dynamical systems and differential equations that we use even to this day come from Poincaré about a century ago. And so the idea is that there are chaotic trajectories in the solar system. And it's pretty easy to understand this. If you think about, I don't know, it's a little hard to see, but let's pretend that that's Earth, and let's pretend that the moon is somewhere over here. Between the Earth and the moon, there is this equal gravity point, this saddle point. It's literally a fixed point of that dynamical system where, and it has saddle eigenvalues. So, it has one positive real and one negative real eigenvalue. And what that means is if I am at this equal gravity point between the Earth and the moon, and I'm perfectly on that point, then I'll stay at that equal spacing, that equal gravity distance between the Earth and the Moon. But if I perturb myself a teeny tiny bit towards the Moon, I'll accelerate towards the Moon. And if I perturb myself a teeny tiny bit towards the Earth, I'll accelerate towards the Earth. And so you can see that at least locally to that fixed point, I get this exponential splitting of my trajectories because of that saddle point. And so that is one of the hallmark features in chaos, is that usually there is some kind of a saddle point that's mediating the stretching and kind of exponential growth of trajectories in that system. Actually, if I go back to this Lorentz system, you'll see that this bundle of trajectories actually stays pretty close together until it gets close to this saddle point here. So it's still on the same lobe, but now they're going to pull down and get close to the saddle point, and that's what causes them to really stretch in this exponential positive Lyapunov exponent way. And I'll mention that this technically, these trajectories don't split the separation between two neighboring trajectories with this sensitive dependence on initial condition, it's not monotonic exponential growth, it's kind of on average exponential growth. Sometimes they come closer together before they move apart, and it's usually driven by how close they get to these saddle points. So saddle points are really essential in this kind of picture of chaos. Again, this is a whole class that I hope to offer at some point in the future, many kind of lectures and hours of content. Here I'm just giving you the very high level, especially as it relates to how do you numerically simulate ordinary differential equations. And so in the solar system, and I want to point out, like, having a saddle doesn't mean you are guaranteed to be chaotic. That just means you locally will have trajectories separate. A pendulum, if I look at the pendulum up condition, that also has a saddle point that, trajectories will kind of diverge locally in time, but in a very predictable way. But if I have enough saddles and I have a high enough dimensional system like this interplanetary, like the solar system network, oftentimes that gives rise to really chaotic trajectories. And it turns out in this case, you can actually harness these chaotic trajectories and harness this exponential growth for very efficient transport to very different regions of the solar system. That's kind of depicted here in this artist's representation, is that if I can get near one of these points where I get this kind of very large sensitivity and this large spreading, then with a small amount of fuel burn, a little delta V of my rocket ship, I can go from, I can jump from this tube to this tube and go to completely different places in the solar system for small amounts of energy. Now this epsilon would be like a small amount of energy allows me to get this large amplification. So chaos is not always a bad thing, but it is hard to predict, and it's hard to simulate, and it's hard to estimate. There are in fact special integrators used to integrate this dynamical system, from our various global space agencies that are supercomputer simulations of what the solar system and all of its objects will look like, at some time in the future. And these are very, very tricky simulations because of the chaotic nature of the system. So another example I like to give in my class of sensitive dependence on initial condition is the double pendulum. So the double pendulum is probably the simplest mechanical system that exhibits chaos. And by double pendulum, I literally mean it's one pendulum with another pendulum attached to it. So there's two thetas, there's theta 1 and theta 2. And this double pendulum, you can picture kind of almost how this thing would swing and maybe do some pretty crazy things. So what I did was I actually built, this was for my first class ever, teaching here at University of Washington, I built an apparatus where I have two double pendulum right next to each other. So it's called the tandem double pendulum. I got this idea from the Controls and Dynamical Systems library at Caltech, where I believe Jerry Marsden had someone gifted a tandem double pendulum. So it's two double pendula right next to each other, and you can start them at the same initial condition. And when you let them go, their trajectories do agree for a little while, and then at some point they diverge because of this sensitive dependence on initial condition. So I built one of those for my class, and that's what we're visualizing here. I start them at the same initial condition and then let go. They're actually agreeing pretty well until they don't. And now they've diverged into totally different solutions. Small changes in the initial condition, small changes in the system parameters, the friction, the length of the pendula will eventually cause these trajectories to diverge in this kind of exponential Lyapunov exponent way. which is really cool. And you can try this thing from different initial conditions. You know, maybe at some point I'll take a video outside and actually, I tried to bring it in here, but the lighting is just not good enough for these. They kind of blend in. And we can try different initial conditions. So for example, if I start with my tandem double pendulum where they're both in the down-down position and I perturb them a small amount, that is not chaotic. They basically will act like little pendulum clocks, and they'll almost perfectly track each other forever until they die out to zero. And I actually chose this initial condition where, you know, one of them was at this kind of 90-degree angle, because that is an initial condition that has enough energy that you kind of excite the chaos in the system. And so that's another key principle here, is that a lot of times for mechanical systems, for the planetary dynamics, there's a certain energy level above which these chaotic dynamics are really excited and activated. And again, it has to do with the saddle points in the system. So in this double pendulum system, the pendulum, if I linearize the dynamics, we know how to linearize the dynamics. The down-down configuration, just the kind of really easy down-down configuration with, you know, small perturbations, that is actually a linear center. It's got plus or minus I omega eigenvalues, and so it's neutrally stable. It's not chaotic. But when I increase the energy, and so now I have the first pendulum arm down and the second pendulum arm up, so kind of the down-up configuration. If I linearize this system, you should do this yourself at home. If you linearize these dynamics, you'll find out that it has a saddle direction in that fixed point. There's one set of plus minus real eigenvalues, and this saddle point is where the chaos comes from. So if I start with energy above this saddle point, I'll get chaotic solutions like this. So that's why I start from that initial condition, because this is where you'll see that sensitive dependence on initial conditions is for energies above this saddle point. We actually just wrote a couple of cool papers showing that the dynamics of this pendulum are almost mathematically identical to the dynamics of the three-body problem that we've been studying, you know, for over 100 years in planetary dynamics, making this double pendulum kind of a cool tabletop experiment to start understanding chaotic transport in the solar system. And again, in both of those systems, we need good numerical integrators, and we need to understand how our error grows through these chaotic systems through this sensitive dependence on initial conditions. Again, that's the key point here, is sensitive dependence on initial conditions. You're going to hear that over and over again. There are other things people use to describe chaos, kind of hallmark features, but that's really the one that I always keep coming back to, is that, you know, a small change in initial conditions often gets amplified kind of exponentially, at least for a while, in these chaotic systems. Good, and you can actually, you know, since I built this about 10 years ago, we've actually built a few much better experimental rigs in the lab. So you can control a chaotic system. So we've pumped in a lot of energy, so it's well above the chaotic threshold. But with feedback control and with a good enough integration scheme, good enough kind of model predictive controller, we can actually swing this pendulum up and stabilize a condition that's normally unstable, and definitely with enough energy that you would classify. If I let the system go, it would have a chaotic dynamic. Okay, this is actually the third generation double pendulum that we built in my lab. I think we're on to the fourth generation now, which is even kind of fancier and nicer than this, where you can do all kinds of cool acrobatic control. Again, leveraging this chaotic dynamics to put in only a small amount of energy at the right time, and using kind of the internal chaotic dynamics to get the system to behave the way you want it to. So really cool stuff. Again, just kind of illustrating that you can, in fact, control these systems sometimes if you're lucky. Okay. Good, so let me think about what else I want to tell you about. So we've talked about how chaotic systems involve this exponential growth of small perturbations. Mathematically, maybe I want to show you actually mathematically how you would write this down, because I think this is pretty useful. So let's say you have your differential equation x dot equals f of x. Now technically this could vary in time as well. This could be f of x comma t, no big deal, nothing's going to change in what I write. It's just a little more complicated. And often what we will say is that the numerical solution x at some future time t is equal to x naught, x at time 0, plus an integral from time 0 to time t of the dynamics f of, and now x is my trajectory. X is my trajectory, which is a function of time. And so you evaluate f at each of these intermediate times from 0 to t along a trajectory, and you integrate this up using a dummy variable tau. Now you can kind of carefully convince yourself, that this is in fact how you would integrate this system mathematically. This is kind of an idealization of what we would do in these Runge-Kutta schemes or Euler schemes. This is like a mathematical expression that if you perfectly did this integral and you perfectly integrated up all of these contributions of f to x dot and kept adding those up along the trajectory, and you kept updating f as x changed, as x moves along that trajectory, then this will step your system forward in time. And oftentimes I call this the flow map operator. Sometimes I call this this big flow map from 0 to t of some x naught, and it steps me forward from t0 to time t. Okay, this is a mathematical object. And what we'll find is that for chaotic systems, so this is actually like one of the first papers I ever wrote. In fact, the first paper I ever wrote when I was a grad student was about analyzing the properties of this flow map when you add a teeny perturbation, when you add a little epsilon to your x. So what I'm going to do is I'm going to say, what if I had, instead of x naught, I had x naught plus an epsilon. So if I have phi, my flow map, I'm integrating from x naught. But what if I have x naught plus an epsilon, plus a teeny tiny little epsilon, a perturbation? And this epsilon could be from a numerical artifact. It could be 10 to the minus 16 round-off error in how I stored this. It could be an order delta t to the 5th error from my Runge-Kutta scheme. Whatever it is, I want to know how that error propagates through this flow map. And so you can Taylor expand this because this epsilon is small. So we can Taylor expand around this is a function. It's a smooth function typically. And so I can Taylor expand. And this is going to equal the flow map that I want, this phi 0t of x naught, plus the Jacobian of this flow map, plus d, let's say d phi dx, 0 to t, evaluated at x naught, times my epsilon, plus I could write out more and more terms, plus higher order terms in epsilon, plus order, let's say epsilon squared and higher terms, okay? And so essentially, this is the true flow map. This is the true trajectory x at time t. This is what I actually want, and this is my leading error term. So this is my kind of leading error term. Leading error. And this is actually how we compute this lambda, at least approximately for finite time trajectories. For finite time t, kind of the leading eigenvalue of, well, the leading singular value of this matrix of derivatives evaluated at x naught is going to give me an estimate of my Lyapunov exponent lambda. Because essentially what this does is this says, this Jacobian, this is a matrix. When I evaluate this set of partial derivatives with respect to x naught, this is a matrix, and I can compute this numerically using things like the finite time Lyapunov exponent. So I have a whole video on that you can check out of how to actually compute this thing and approximate it from trajectory data. But the long story short is that this is a matrix when I evaluate it at x naught, and it tells me that that matrix has, eigenvalues and eigenvectors and singular values and singular vectors. There are directions that that matrix makes bigger, and there's directions that that matrix makes smaller. And so if my error is aligned with one of the bad directions of this amplifying matrix, then my error is going to get amplified. And so what we find is that this matrix has, oftentimes for chaotic systems, this matrix will have large singular values, meaning there are directions that if error is in that direction, those will get amplified exponentially. And so what you do mathematically, I'll just write this down in case you're curious. You don't have to understand all the steps. There's a whole video and a whole papers about this, is that you could basically pick the max singular value of this d phi dx, and that is going to equal, essentially, approximately this e to the lambda t. So you could approximate your Lyapunov exponent lambda by taking the logarithm of the maximum singular value and dividing by the integration time t. So that gives you a way of estimating how this error propagates through your system. And this kind of synthesizes a lot of things we've thought about in this series on differential equations. So this is the perfect trajectory integration scheme. If I had infinitesimal truly dt delta t's, like truly calculus infinitesimal dt's, this would be exact and true. This would give me the trajectory at any point in time. But we know that we're chopping up our trajectory into finite delta t's that accrue some error, some epsilon error. And so if I assume that at each time step I introduce this error epsilon, maybe it's even 10 to the minus 16. Maybe I have an amazing integrator and it's as good as my computer can represent numbers, but I'm still going to have some representation error 10 to the minus 16 at the best case here. I can Taylor expand that out, and I get these interesting terms from my Taylor series where I can isolate that this is the leading error term. And the point I'm trying to make is that for chaotic systems, this leading error term amplifies like e to the lambda t, okay? Which is a big deal. That's really bad. That means that even my 10 to the minus 16 error is going to amplify and stretch and grow. And so there's ways you can control that, and there's ways you can understand how big that lambda is numerically using these finite time Lyapunov exponents by actually computing the singular value decomposition of this, or if you like, the eigenvalue decomposition of this times its transpose, the Cauchy-Green stress tensor. So I think that's pretty interesting. Something else I think I want to tell you about is if I take a mechanical system like this double pendulum, so in fact, exactly like this double pendulum, let's assume that there is no friction on these bearings. So we're going to make an idealized, perfect Hamiltonian system or Lagrangian system with no dissipation. We know that the energy should be conserved in this system. Okay, so if I literally plot, energy versus time, there should be a constant line for any trajectory that I integrate starting from x naught to some xt. That energy should be constant. Now this is actually a really good exercise. You should write down the double pendulum equations of motion. You can do this from the Euler-Lagrange equations or from the Hamiltonian equations. Pretty easy to do. It's a little messy, to get all the sines and cosines right, but it's not so hard. And you should write down an RK4 integrator for that problem and simulate that trajectory forward in time and compute the energy at each time step. And what you'll find is that the energy of the RK4 is going to be a mess. It's going to diverge from this constant. Maybe it'll go to negative infinity, maybe it'll go to positive infinity, but it's not going to be a constant. It's far from a constant. When you integrate these mechanical systems, basic fundamental conservation laws like conservation of energy are being violated, and like truly violated here. I feel violated when I integrate a system that should be conservative with an RK scheme, and you should too. And so there are better numerical algorithms for integrating these kinds of chaotic systems if there's that additional structure. If we know that our system is Hamiltonian, so for Hamiltonian systems, Hamiltonian, there are integrators called symplectic integrators, symplectic. And they essentially, let's say symplectic integrators. There's some really good algorithms out there for symplectic integrators, where essentially we know that Hamiltonian systems generally have this kind of skew symmetric structure between positions and momenta, so that you have some skew symmetric structure like this in your equations. And what symplectic integrators do is that they build the numerical updating scheme so that every time step this structure is exactly preserved. So if you like, all of these errors, even when they accrue, they are still being kind of projected back onto a manifold where the basic physics, the basic energy conservation is being satisfied. So those algorithms, like a symplectic, maybe I'll make this in green, something like symplectic, even when the integrator tries to, pull it off of this energy surface, it's kind of constantly correcting it and staying very, very close to that energy surface. So these are really, really important if you want to integrate, a spaceship through the solar system, or if you want to know how a space rock is going to be hurtling through the solar system, you better be using a smart integrator or else you're going to get garbage. You're not going to know if it's going to hit Earth in 50 years or not because your simulator is completely off base. Okay, just like there are symplectic integrators, there are also, and that preserves Hamiltonian structure. If you have something that is, if you want to start from the Lagrangian, which these are kind of equivalent, ways of representing mechanical systems. The Euler-Lagrange equations, if you want to discretely in a computer integrator satisfy the Lagrangian, the Euler-Lagrange equations, these are called variational integrators. Variational. And I might, I spent a lot of time developing variational and symplectic integrators in research, and back, a decade ago, maybe I'll have a whole video on variational and symplectic integrators because they're so important for integrating hard chaotic systems where you really need to know good trajectories, good answers for a specific initial condition. Again, in that Lorentz case I was showing you, I just wanted to know kind of the statistics of how things happened. And so it didn't really matter. I didn't care about that single trajectory and where it went as much as the statistics. But if I'm following an asteroid or a space rock in the solar system, I really want to know that specific trajectory where it's going to be. I need these better variational and symplectic integrators. Now it turns out, kind of a fun happenstance, that an RK78 integrator, this is sometimes called the RKF, the Runge-Kudde-Fehlberg 7-8, RKF78. It turns out that RKF78 is nearly symplectic for lots of problems, and so it's actually an amazing integrator. It has kind of all of the properties of an RK integrator, very small single-step errors, so very accurate on single steps, and it approximately is symplectic on lots of problems. I couldn't tell you why, to be honest. This is something I've heard people say, and I've observed it myself, that when you simulate these chaotic systems, this tends to work much, much better than this. Because of some structural property here. So that's interesting too. Good. Yeah, so this is really important. And you sometimes need these better integrators, again, for things like control applications. I can't have my energy blowing up in my model prediction. For really tricky prediction problems, I can't have my error blowing up for these systems. Okay, good. Maybe I'll just point out a couple other examples that I think are really cool. So I'm going to bring up some more videos. I'm going to erase this really quickly and then bring up those videos, and then I'll conclude. And I'll also point out, I got this interesting advice once when I was an undergraduate that, a human life is also chaotic. It feels very chaotic sometimes. Sometimes it feels more deterministic. Sometimes it feels fully chaotic. But, the choices you make can often have these large kind of divergent effects, right? So this is, it's an interesting meta perspective that, small changes to what you do can add up to large changes over time. And so, understanding, having some model predictive control, understanding where you think you're going and where you want to go, and figuring out, am I at one of these critical points where things could go totally differently? And, in those cases, I'm going to slow down. I'm going to decrease my delta t. I'm going to think harder about what decisions I'm making. So anyway, kind of interesting. I thought that was fun. This was at like a cocktail party when I was an undergrad, and Jerry Marsden told me about, like the butterfly effect and how decisions, you make now can make a big difference later on, and he was absolutely right. Okay, so some other cool examples. Fluid flows are often chaotic, and so specifically turbulence. When someone talks about turbulence or a turbulent fluid flow, often we model that turbulence as a chaotic dynamical system. So there is a deep, deep relationship. For many decades, researchers in turbulence have studied chaotic dynamical systems, and researchers in chaos have used turbulence to motivate what they're doing. I feel like I'm getting a little bit trapped here. And so this is a cool example of a thermal convection. You have a hot plate on the bottom and a cold plate on top, and you get this kind of thermal convection. This is actually exactly what Lorentz was studying in this Lorentz 1963 model, was the chaotic convection in the Earth's atmosphere. So, the noonday sun, let's say you wake up in the morning, the sun starts beating down on the plains, it heats up the plains, and it creates these large thermal convection patterns You often get big thunderstorms and supercell clouds and things like that. And this system can be at least approximated by this chaotic differential equation on the right. And so this was observed that similar conditions from day to day, starting conditions, can often lead to very, very different cloud formation and weather formation and precipitation and all kinds of things that are captured in this model. So this uncertainty and sensitivity of chaotic convection was captured in this 1963 Lorentz model. I always add Fetter and Hamilton, Linda Fetter and Margaret Hamilton, when I put this author list down, because they were the grad students who actually ran the simulations that Lorentz used to build these models. By modern collaboration standards, they would almost certainly be co-authors on that work, and I don't think we should forget their contribution to this extremely important chaotic dynamical system that we all use. And more generally, in fluid dynamics, you can kind of picture how this chaos arises if you think about sensitive dependence on initial conditions. This is super cool work by the KTH group. I love this video. I've used this video before, and I'm a huge fan of their simulations and their work, where they simulate this super, super high fidelity numerical simulation of the turbulence over wings and things like that. And so the fluid flow itself is chaotic. If I perturbed one of these vortices by even a little bit, the flow, the exact configuration would change quite rapidly and give you a totally different distribution. Sorry, it would give you the same distribution of vortices, but a different instance, a different realization. This vortex might be over here, and this one might be over here, and things like that. So small changes in the flow field itself will cause the flow field to change over time. Things get amplified as it goes through this flow. And down here, small changes up here will have big changes down here. That's one interpretation of chaos. Another one that I like is, imagine you're a little particle. This is kind of fun. We're a little particle, and we're in this flow. If I start one epsilon to the left or one epsilon to the right, I'm going to get pulled into a whole different network of vortices, and my path is going to be completely different, even with a teeny tiny epsilon perturbation to my initial condition. So a lot of chaos in this system as well. And this is where I want to point out, when I was kind of growing up in dynamical systems, I was deep into this three-body problem, solar system dynamics, planetary dynamics, fluid dynamics, where chaos is just a part of our life. It's everywhere. And I kind of thought to myself, well, how could you possibly have a high-dimensional dynamical system with x dot equals f of x that wasn't chaotic? And I met some friends in grad school who had high-dimensional dynamical systems that were, in fact, very much non-chaotic, and they actually kind of self-organized and self-ordered. If you think about it, your body is an incredibly high-dimensional dynamical system. And although there are aspects of chaos locally, it's extremely well regulated and ordered, and kind of these emergent patterns reinforce and persist, right? Like your metabolic regulation kind of says that at least those variables are not diverging. You can eat a Snickers bar, or I can skip lunch, and typically, those perturbations don't cause my system to go completely chaotic. Sometimes they can, certainly, but you have a lot of kind of stability and determinism built into this very high-dimensional system. So clearly, chaos is not a universal property of all dynamical systems. So even in really, really complicated fluid flows, oftentimes you get these coherent structures, these patterns that keep coming up and keep forming over and over again, even in very turbulent flows. That this is locally chaotic, but there are these large-scale emergent synchronizations and patterns. This you can see, I think this is a great example. This flow, this is an atmospheric flow past Guadalupe Island, where again, this is a chaotic system. We know that weather is chaotic fundamentally, and fluid flows in general are also, but you still get the emergence of these large-scale structures. And so one of my favorite videos is this metronome synchronization video. So I've been playing this for my class for the last 10 years. I love this video, where you basically have this initial condition. So someone comes in and they start all of these metronomes, these little pendula at different initial conditions. And so that's totally disorganized. And I'm going to turn up my volume here because I kind of actually want you to hear all the clicking. They're all over the place. And you'll notice that they're on this kind of table that is loosely able to vibrate. So sometimes the example I've seen, you can build one of these at home. You take 2 cans of soda, Coke, and you put a little plank on top of it, and then you put your little metronomes on top of here, and the weak epsilon coupling between these, because the plank can roll on top of these cylinders, will eventually cause these to synchronize. And so and this is a common phenomena in lots of high-dimensional systems that are weakly coupled. Let me keep watching this. So at some point there's going to be a phase change where they start to synchronize. It's almost happened. You can almost see now like half of them have started to synchronize. And some of them are out of phase, but they're definitely starting to synchronize almost. And it's almost happened now. And the more they synchronize, the more they synchronize. So this table, you can actually see the table wobbling now. Now it's giving a very strong forcing, keeping them all synchronized. And this guy over here, this one's my hero. That one's going to take the longest to synchronize. That one over there is going to take the longest to synchronize. So it doesn't, some of these will take a little while. But you can see that this emergent behavior does exist in these systems. And sometimes all it takes is a little epsilon coupling so that you get this feedback to kind of bring them into synchrony. So, we've known for a long time when soldiers cross a bridge in formation, they're supposed to break their marching cadence, or else they could bring the bridge down. This has been known for a long time. You're supposed to break step when you cross bridges in large groups. The Millennium Bridge in London, that really cool bridge, walking bridge with the cool cables, that had a weak coupling so that when people walked across it, when one person stepped, and it caused the bridge to move a little bit to one side, everyone else braced themselves out of phase and caused another force, and those eventually caused everyone to synchronize just like this, and that almost broke the bridge down. Everyone had to drop on all fours and crawl off because of this kind of emergent synchronization. So I guess the point I'm trying to make here is that high-dimensional dynamical systems can be chaotic, they can be deterministic, they can synchronize, they can desynchronize. There's a lot of super duper rich phenomena in these systems that you can observe and predict and estimate and control. But really understanding how the numerics works and how you would simulate these in a computer, how small perturbations can grow exponentially, those are all really, really important. This is a rich field. It's one of the most interesting fields in all of mathematics because it ties together differential equations and linear algebra and numerics and computation and physics, and it explains and allows us to describe the world that we observe around us, which changes in time and evolves according to rules and has instabilities and synchronizations and all of it, and it's super fascinating. I'm glad you have been with me on this series, and I hope that there are more and that you get interested in following in some of these leads and threads. Thank you all so much.